Now let's consider the intermediate form HL, which is called MP-protic. Okay, MP means both sides. Okay, you know the word amphibian, right? Like a frog. Okay? It can live in water and also in the land. Okay. Anyway, uh, this form is called MP-protic. That means it can produce protons, or it can take the protons from water. Okay, so it can act as acid, or at the same time it can act as a base. Okay, and then our question is, well, how do we calculate pH when this is dissolved in water? Okay, but here you see this one, this dissociation constant of for this equation is that 10 to minus 10, right? So we say that this one, HL, is a quite weak acid. Likewise, we can determine uh, how weak this HL, how weak a base, yeah? For the Kb for this second this equation, Kb is 10 to minus 12. Wow, this is also very weak base. Yeah? But only from these two equilibrium constant we can decide whether the solution is acid or basic when this HL is dissolved in water. Since Ka is greater than Kb, okay, anyway, the solution becomes acidic when HL is dissolved in water. But how do we exactly calculate the pH? Okay, and then we have to develop a theory about this intermediate form. All right. Now let's apply this charge balance equation. Okay, when HL is dissolved. On the left hand side, we write all the um, partially charged species, okay, which is only proton and H2L plus here. Okay, on the right hand side, we write the negatively charged species, which is L minus and hydroxide ion only. Yeah, this is it. And then we rearrange this equation, like that, by moving this right hand side, or this concentration to the left. Okay, and then using K1 and K2, we can rewrite the this fully protonated form, right? Which is HL multiplied by proton divided by K1. Okay. Likewise, for L minus, we can uh, write again using K2, yeah, which is given by this one, right? And then proton here, and then for hydroxide ion, well, we write in terms of proton concentration using Kw. Okay, yeah, this one. And then this is if we multiply the proton concentration on both sides, and it becomes what quadratic equation, okay, in terms of proton concentration. Yeah, here this quadratic equation is very easy to solve, right? Then finally, we reach it this equation, okay, this one. Proton concentration is represented by this equation, okay, square root of rather complex form inside, okay, here. And you remember this one, this equation, we reach it finally this equation. This equation, uh, we don't we didn't make any assumption, so this equation is a very precise equation. Okay, so uh, if we know the concentration, and I mean the equilibrium concentration of HL, and then we can calculate proton concentration. But question is, how do we know the equilibrium concentration? Yeah, there is a way. Then you will see soon. Yeah, but in most cases, comparing, yeah, this one HL, equilibrium concentration, and this one, formal concentration of compound HL. And then, since look at that, in this case of Liu-Shin, and this dissociation constant are very small, very small. That means what? It is not very well dissociated. So in this case, we can have a very good, approximation. This equilibrium concentration is almost the same as formal concentration here. Okay. Now instead of this one, we use F formal concentration, right? Formal concentration, yeah, we simply we measure the exact mass of HL and we dissolve in solution, right? This is first approximation, okay, for proton concentration for this intermediate form. All right. Here is the example of Liu-Shin. Yeah, the formal concentration of Liu-Shin is 0.05 molar. Okay, what's the pH? Yeah, we use this approximation, and yeah, we solve this equation, and then we got 8.76 times 10 to the minus 7 molar, right? And pH is 6.06. Okay, so our we from these two equilibrium constant, we immediately knew that when HL is dissolved in water, and then solution may be acidic, but we don't know how much acidic. Okay, here, right? We now calculated the pH is 6.06. Okay, it is acidic, all right? And then now calculate, the other forms, okay, from the proton concentration. Okay, the first H2L form can be calculated from K1, okay, using this one, and we simply use the formal concentration of HL, right? And then we got 9.34 times 10 to the minus 6, okay? Yeah, this is much smaller compared to the this HL form, HL concentration. Likewise, we can calculate, the fully protonated form concentration using K2, and then we get about 10 to the minus 5 molar. All right. Yeah. So our initial assumption is good. Okay. So this assumption is a good approximation because these two species are so small. Okay. Right. Let's further simplify this equation. All right. And this is the first approximation. And in many cases, you see, look at that's a numerator. All right. So the numerator, this one Kw, yeah, you see, this is 10 to minus 14. It's very very small value, okay. And if K2 multiplied by this F is much greater than Kw, and then we can ignore this one, this term, all right. And also, if when we compare K1 and F, and in many cases, what F is much greater than K1. So in this case, the denominator, we can ignore K1. And then, the proton concentration is simply square root of K1 and K2. Okay? This is the second approximation. All right? So when you take a logarithm on both sides, then we get the pH is simply the one half of sum of pk1 plus pk2. Okay, yeah. Okay, this is second approximation. So now I stress again that we can make a first approximation, by equating the equilibrium concentration is equal to formal concentration, and second approximation, we can go further, then we get this one. We reached this very simplified equation. All right. Okay, now let's go on to calculate each component's concentration when uh, this one this intermediate form is dissolved in water. Okay. Uh, okay, let's take on take the solution case again. Okay. Okay, question is the concentrations of this polyprotonate form and polydiprotonate form. Okay, when the solution intermediate form is dissolved in water. Okay, and then we already calculated here the proton concentration is 8.7. Let me see, right around here. Okay, and 8.80 this time. I think this is more accurate. Times 10 to minus 7, and simply we make an approximation of HL, equilibrium constant concentration is the same as formal concentration. Using K1, we calculate H2L plus, okay, which is 9.36 times 10 to minus 6, okay, and L minus is this one, okay. And here, and we already, calculated the Leucine, when we started fully protonated form, right? In the case, the pH is 1.88. Okay, let me show you again. Here, pH is 1.88, and then fully deprotonated form, yeah, when pH is the in the case pH is 11.21. Okay, yeah. So this is, although I write this way, actually this is H2L plus. Okay, this is L minus. Okay, and for the intermediate form, yeah, our pH calculation is 6.06. Okay, in that case, we can calculate it already for individual, you know, the species, right? Yeah. So now you understand. Okay. Let me see. In this case, maybe this one uh, is maybe is wrong. Let me see. For the poorly proteinated form, um, HL form, yeah, concentration is given by this amount. Okay. Yeah. So things may be very simplified, but we we will meet the very different situation. Okay, I will treat in a separate lecture. Okay.